everyone, and thanks for watching Edupedia World videos. In this video, we'll begin a new topic of the phenomena of reflection of light, and the first part we'll study is reflection at plane surfaces. We've already derived the formulas for reflection of light previously using Huygens principle, so I'm just going to write them down. If this is a plane surface, these markings I'm drawing represent that the smooth surface, that is the upper surface of this plane, is the reflecting part. And there is a ray of light that is incident, then it gets reflected somewhat like this. We draw the normal. The normal is the line through the point of contact and perpendicular to the surface. So this is what the normal would be. This angle is called I, the angle of incidence, that is the angle which the incident ray makes with the normal, and this angle is called R, the angle of reflection, and it is the angle which the reflected ray makes with the normal. Right? So the first law of reflection of light from a plane surface, or actually from any surface, but we are specifically studying plane surfaces now, says that the angle of incidence is equal to the angle of reflection. That means I is equal to R. We've derived it using Huygens principle, right? The second law tells us something about the direction of the light. So for example, let's say now we are looking at a top view. This is our eye, and then we'll see a surface like this, and the incident ray might go like this, top to bottom, and the reflected ray will come out like this. But it's also possible that the reflected ray turns and goes like this, or like this, or like this, while making the same angle with this, right? So it doesn't need to be in the plane of the monitor, it can be in any place. That theoretically could be possible. But to tell us that that is not indeed true, the second law of reflection states that the incident ray, the normal, and the reflected ray lie in the same plane. This might seem obvious to you. There really is no reason why this incident ray should turn inside or outside the plane, but this second law makes it proper. It just tells us that without this second law there was a possibility that it would turn, but it indeed does not turn, and therefore the incident ray, the normal, and the reflected ray lie in the same plane. By the way, the normal is referred to generally as normal at the point of incidence. This is the point of incidence, but I'm just going to say normal, and normal would mean automatically the normal at the point of incidence. So let's see how the image of an object is formed in front of a plane mirror. Now I'll take a vertical plane mirror. This is the mirror. The left side is the reflecting side. Let's say I keep an object here. Right, so let's draw first of all the easy lines that we know, the bottom of the object. And by the way, this you should pay close attention to, because this is the same way we will create an image using a picture in spherical reflected mirrors and in lenses and in refraction at spherical surfaces as well. So the concept will stay the same. We take one ray that goes straight along, and since it is that originates from the bottom of the figure, bottom of the object, and since it strikes the plane at a 90-degree angle, it is reflected back, right? And if a ray is reflected back from this point horizontally, then it would seem to us that the ray was coming from this point, right? From this side perpendicular to the surface. Similarly, we could draw another ray going perpendicular to the surface like this, and it will be reflected normally and come back like this. We could extend this like this. Similarly, this ray could be extended like this. So it seems to us, because of normal incidence, that this reflected ray is actually coming from a point beyond the mirror, and this reflected ray is also coming from a point beyond the mirror. Right. Now let's look at the interesting one. Let's say the top part of this object is reflected from this point. So the incident ray will go like this. This will be the angle of incidence. The reflected ray will come back like this. This will be the angle of reflection, and we know I is equal to R. So this reflected ray, it will seem like an observer that it is coming from a point that is extended beyond here. right? And where do these 2 points meet? These 2 points meet here, and this point is the image of this point due to these 2 rays. And if we actually take another ray arbitrary like this, going back like this, you'll actually theoretically be able to prove that it also intersects at this point. So all the images due to different points of this mirror of the object that is the top of this object will be created here. Similarly, you can try to figure out that all the images of this point, the lowest part of the object, will be here. Hence, it will seem to us that these reflected rays are coming from an object like this. Now these two lines are parallel. This is 90 degrees, so this is 90 degree. This is R, so this is R. So these two angles are equal. From that we can tell that these two triangles are congruent. That means that this distance is equal to this distance and this height is equal to this height. So for a plane mirror, the distance of the image from the plane mirror is the same as the distance of the object from the plane mirror, just on the opposite side. And also the height of the image is equal to the height of the object. The second term is called magnification, and its definition is height of the image by height of the object. And so since this height is equal to this height, we can prove that the magnification for a plane mirror is 1. Right? So plane mirror is simple enough. Now let's move on to a little bit more complicated issue, the issue of spherical mirrors. So let's just say this is a spherical mirror. What that means is that there was a sphere and we just cut off part of that sphere and we discarded this part, and whatever was left we silvered the outside, so the inner surface became reflecting. So this part of the mirror is actually a part of a sphere, and that is why these types of mirrors are called spherical mirrors. They can be of two types, concave and convex. This is called a concave mirror, and a mirror of this sort, in which the outer bulging surface or the convex surface is the reflecting surface, is called a convex mirror. Okay. And both of them have been cut from a sphere. Let's say the sphere has a center here and this was the original true sphere from which this was cut. Then this radius of the sphere from which this mirror was cut, R, is called the radius of curvature. So these are three important quantities. You have convex mirrors and concave mirrors depending on what side of the mirror is silvered and what side of the mirror reflects. And you have the radius of the sphere from which this mirror is cut, and such a radius is called the radius of curvature. Now there is one more important quantity as it relates to mirrors, and that is the focus. Now there are two types of focuses for every spherical mirror. And okay, wait, before discussing focus, a small concept needs to remain, and that is the sign convention we will be using. So the sign convention is this. Here you could have either a concave mirror or a convex mirror, it doesn't matter, so I'm not going to draw which side is reflecting right now. Let's say you have an object like this and incident rays go like this. We'll learn how to draw the image properly in a second, but right now we're focusing on the signs we'll use to make our formulation and make our formulas easier. Now, if the object is placed on this side and going here, then this has to be a concave mirror. If this was a convex mirror in which the right side was reflecting, then we would have kept an object here. Right. Now, the first sign convention is that the positive direction, positive x direction, is in the direction of incident rays. So whatever axis we choose, the right side will have to be taken as the positive x-axis. That means the left side will have to be taken as the negative x-axis. Now what is the origin? That is the second point. It should have come before this actually. And the origin is the pole. Now what is the pole? This particular line, the line joining the bottom of the image to the point where it's being reflected to somewhere, the center of curvature will also be on this line. This line is called the principal axis. Now the principal axis is perpendicular to this mirror where it meets. This is not clearly shown in this figure, but the principal axis is supposed to be perpendicular to the mirror at this point. Right. Now what is the pole? Pole is the point of intersection of the principal axis and the mirror. By the way, almost similar formulas will be used for lens. This will be lens here, this will be the direction of incident rays for lens. The lens also has a focus and so on. So once we learn these concepts properly, it will carry over very easily to lenses. So this is the principal axis, this is the mirror. What is the point of intersection? This is. So this is called P, the pole. So this is the origin, this is the positive x direction, this is the negative x direction. The third convention, vertically upwards is positive and vertically downwards is negative. Now when we talked about magnification a minute earlier, it was height of the object by height of the image, but from now on just remember that height of object, height of image, object distance, image distance, even though we'll say distance and height, we still mean with the sign. So the magnification is height of object by height of image with the sign. So when we did it for a plane mirror, this was the object and this was the image, and both of them were vertically upwards. So both of them had the same sign, so the magnification was 1, or in fact plus 1. If this image in turn had been vertically downward and of the same height, then the magnification would have been minus 1, because the magnitudes of these two are the same, but this would be positive and this would be negative. Right? So the coordinate sign convention is very important. The pole will be the origin, that is the point of intersection of the principal axis and the mirror. The positive direction will be the direction of incident rays. If we had kept our object here and this was a convex mirror where this was shiny surface and this was the reflecting surface, in that case this direction would have been the positive direction and our x and y coordinates would have been reversed. So now that we've done with most of the terminology, now we begin our study of focus. So I'll do it for both convex and concave mirrors so you can see the difference between the two. So this is I'm drawing the principal axis. Now the principal axis should be perpendicular. This should be almost perpendicular. So if a ray goes along the principal axis, it should be reflected directly back. Right. So we know the array that is going along the principal axis like this will be reflected directly back. Right. What about other rays that will be parallel to the principal axis? Right. So let's consider this ray that is parallel to the principal axis. Now the laws of reflection are the same for spherical or plane mirrors. The reflected ray and the incident ray and the normal are coplanar, and angle of incidence is equal to angle of reflection. How do I figure out angle of incidence and angle of reflection? If this is, let's say, a mirror we have, then at any point we can just draw the tangent, and the perpendicular to the tangent will be the normal. So if a ray goes like this, it will come back like this. So making a normal is easy enough. Just first make the tangent and then make the normal perpendicular to the tangent. Right. So let's say we do that sort of thing for this ray. This will be the normal, this will be the tangent, and this will be the normal that is perpendicular to the tangent. Right. By the way, where will the normal intersect? The normal will intersect at R, where this will be the radius of curvature. Because we know any line from radius to the sphere will be perpendicular to the sphere. It will be perpendicular to the tangent. Right. So it will be a normal. So this is R. If this ray gets reflected about this normal, then it will go back someplace like this, such that this angle is equal to this angle. Now if you take another ray that goes like this, parallel, the same thing will happen and it will be reflected back. Now sometimes it may be reflected like this or like this, but this is a very special case in which the rays all intersect at the same point on the principal axis. Right, and that is when these incident rays are paraxial. Paraxial means they are close to the principal axis. What that basically means is, if this is a true spherical mirror, then we will only be considering rays going like this and like this and like this. they'll all intersect at the same point. We'll not consider a ray going like this. It might just fall down somewhere like this, and it will not intersect at the same point, and it will make things more complicated. So while we are doing the mirror formula and lens formula, we'll make many assumptions, and those assumptions will all come from the fact that we are assuming that all the incident rays are paraxial. That means they are close to the principal axis. This distance is quite small compared to the radius of curvature. So if incident rays are paraxial, then they have an interesting property. Then all incident rays parallel to the principal axis meet at the same point, and this point is called the focus. Right. And this length is called the focal length. Just like this point is called the center of curvature and this distance is called the radius of curvature, this point is called the focus and this point is called the focal length. So the focus can be described as the point where all paraxial incident rays parallel to the principal axis meet the principal axis. They all meet at the same point. If they come parallel to the principal axis and are close to the principal axis, they'll meet at the same point, and that point is called the focus. Now, it's a little bit different for convex mirrors. What happens with convex mirrors is this is a ray, then this will be the tangent, this will be the normal. So the ray will be reflected something like this. And if the ray is reflected like this and there's another ray, and that will be reflected like this, then all these rays, they'll not intersect at any point, but if we produce them backwards, it will seem to us that they will intersect at a point, and that point is also called the focus, and this length is also called the focal length. Right. So for a concave mirror, incident rays which are parallel and close to the principal axis, they will actually meet at a point. They'll all meet at the same point. That point will be the focus. For a convex mirror, the incident rays which are parallel to the principal axis and paraxial, they will never intersect, but they'll appear to diverge from a point behind the mirror if we extend them. And this point will again be called the focus. Now, there's a slight bit of terminology somewhat confusing, so I want to make that really clear. There are actually two focuses for each mirror. Right? One is called the first focus and one is called the second focus. And the more important focus, the focus that is generally used in mirror and lens formulas, is the second focus or the second focal length. The second focus would be the point, distance from the pole would be the second focal length. And that is what we've discussed up till now. These two are the second focus. Right. So what is the definition of the second focus or of the second focal length? It is the point where the parallel rays will either intersect or appear to diverge from. Right. The other type of focus is a point where an object can actually be kept so that the final rays are parallel to the principal axis. So now I'll just show this for the concave one first to make this clear. This is a concave mirror. And the convex mirror will come easy enough to you after this. So the way I remember it, the easy way is that the second focus, this is by the way unnecessarily confusing and I don't know why they named it this way, but the second focus is the focus which is more important. When you say 1 by v minus 1 by u is 1 by f or 1 by v plus 1 by u is 1 by f, that f is the second focus. And the second focus is the image distance, which is also called v, when the object distance u is infinity. I'm sure you've seen u and v before. So the second focus is the image distance when the object distance is infinity. What does it mean to say the object distance is infinity? It means the object is very far away and rays are coming paraxially. Right, and they are coming parallel to the principal axis. In that case, they'll all meet at the same point. Sorry, they're supposed to meet at the same point, but I didn't draw the figure very nicely. And that point will be called the second focus, and this length will be called the second focal length. Right. Now, let me just make a table here. First focal length and second focal length. For a concave mirror, what do you think is the direction or the sign of the second focal length? Yes, it's negative. Because the second focal length, remember, the direction of the incident rays is taken to be positive. So the right side is the positive side and this is the origin. If this is the origin and the right side is the positive side, then this length, if it is 2 meters, then the second focal length will be minus 2 meters with the sign. So the second focal length is negative. Right. Now we need the first focal length for a concave mirror. The first focal length would be the object distance, or U, when image distance is infinity. So in the first case, we want parallel rays coming and we want to find out where they meet. In the second case, we want to find out from where do the rays diverge so that the reflected rays will be parallel. Now it's easy enough for a mirror. If these parallel rays meet at this point, then rays which will be diverging from this point traced backwards will emerge parallel. Right. So this is an interesting concept for mirrors, and that's why I really stressed on this earlier. The first focal length is also negative and they're the same. For mirrors, the first focal length and the second focal length have the same direction, same sign at the same point. When we move on to lenses, it will get a little bit more tricky because they will not be same. For lenses, if the first focal length is negative, then the second focal length will be positive. However, that is not the case for mirrors, and that's why I wanted to introduce this concept in the beginning as well. Right? If you have convex mirrors, then parallel rays will diverge like this and they'll appear to diverge from this point, which is the focal length. Right? So it is positive. Incident rays coming from infinity will meet at a point that is towards the right of the pole, so it's positive. If there is an object here, right, now this gets a little bit tricky because there can't be an object really here, because then it would not be reflected from the shiny side. However, if there was, let's say, somehow, it's not important how we create this, that you'll see later in optical instruments, but somehow we have the object in which rays are converging to a point. This is not coming from one particular object, it's just somehow we've arranged rays to come to this point such that if there was no mirror, they would have converged at this point. And this point is such that all these rays end up parallel to the principal axis. Then this is called the first focus, and again you can see that it's positive. Right. So for a mirror, first focus and second focus are the same. However, the definitions are still different. First focus is the object distance when the image distance is infinity. Second focus is the image distance when the object distance is infinity. And once we reach lenses, you'll see that these two don't really give us the same result. Okay, I think that's enough for this video. In the next video, we'll actually derive the formulas 1 by V plus 1 by U is equal to 1 by F, and the magnification formulas which you've seen earlier for a spherical mirror. We'll do it for a concave mirror, but it can be generalized easy enough to any form of spherical mirror. Right. So the things we've learned in this video: laws of reflection and refraction, refraction we haven't done yet, and more importantly, properties of a mirror. The sign convention: the pole is the origin, direction of incident rays are the positive direction, vertically upward is the positive direction. Second focus, point where parallel rays meet. First focus, point from where rays should diverge so they emerge parallel. For mirrors, they both are exactly the same. For lens, they'll be on either side of the lens and they'll be the opposite. Right? Thank you.